Good morning. Today's lab, we're going to be looking at mutual inductance. So this is a pretty interesting effect. What it says is that we can get charges accelerating in one part of a circuit, and those charges that are accelerating will actually have an effect on charges in a circuit that's actually distinct. This is kind of, it's a transformer, right? In class we talked about transformers and how there's a primary and a secondary to the transformer, and if charges are being accelerated, if charges are accelerating in the primary side, then that's going to have an effect on the charges in the secondary side. Now, the amount of mutual inductance, the coupling that takes place between the two sides in a transformer, for example, it depends on how many loops we've got. It depends on how close the two loops of wire, the two sets of wire are placed. So it's going to depend on the lengths and the number and the radiuses and the proximity of those two. So I tried to diagram this as clearly as possible. Let's say that we start with an AC power supply, and we've got one right here, and we run some wires out, and we connect that to, well, it's a solenoid. And so what I did is I brought out one of our big solenoids with the 3,250 loops. Yeah, that's one of the big guys. And I connected wires to it. Now what I want to be able to do is, it turns out for the primary circuit, I want to be able to keep track of current, how much current is being generated. Now, so I put an ammeter in here. Now, remember the ammeters, you got to make sure that when you're measuring the current, that there's plenty of resistance, and that's what we've got here. We've got a lot of resistance. We actually have a fair amount of what we call impedance that we'll be seeing with AC circuits, maybe in the near future. So there's a lot of resistance here. We're going to be okay. The voltage here that I'm using is 6.3 volts. Once again. Now this is at, the frequency is going to become important. So this is operating at 60 hertz. And remember, we don't want to work in terms of hertz, we want to work in terms of radians per second. So when I take the 60 hertz and multiply by 2 pi, I get 377 radians per second. So here's the power supply. Here's the circuit that we've set up, and I'm going to measure how much current I'm getting. And I guess I could do that now. I'm going to turn on my, I've wired everything, I believe it to be correct, and I'm going to turn this on, and it's got to measure AC. I always forget that last step. There we go. So I switched it over into AC, and I'm getting 23, 24, 25 millivolts, something like that. 23 millivolts it's reading. And so I'll turn this off. So what we can do now is look to see if setting up the AC charges in this, the AC current in this circuit is going to set these charges into motion. And if it sets them into motion, one thing that I could watch for is I can watch for the voltage. We actually want to look at the current in the primary circuit and then the voltage in the secondary, and we'll take a look at the equations and see why that is. But here I've got another solenoid. Now I could place this really close, or I could place it farther away. I actually cut off the edges of this so that I can actually slide it right in so that they overlap. I'm thinking that's going to be the best mutual inductance, is if I could just have these two completely overlapped. Then when these charges accelerate, they're going to generate large enough electric fields that they're going to set these other charges into motion. So let's see if that happens. I'm going to turn on the voltage here. Turn on the voltmeter, sorry, not the voltage. I'm going to turn on the voltmeter. And also set this to AC. And I'm going to turn this on, and sure enough, right, I'm getting a voltage, a few hundred millivolts over here, that's being set up. Now, if I take this and move it out, I can see that it drops off. So what we want to do is, we just want to map that out. We want to map out how does the mutual inductance, at what rate does it drop off as we increase distance. Now I got to decide how I'm going to measure distances between these two solenoids. So what I'm going to say is this. I'm going to say when they're centered like this, it's 0. It's from the central plane on one to the central plane on the other. And right now that's at 0. And then I'm going to move it a couple centimeters at a time. So I move this 2 centimeters, I'll move it 2 more centimeters, and we'll see. I mean, I'm going to take a series of measurements here, and once we get out to where it's just dropping down to 0, I'm not going to worry so much about it. But I'm going to get my ruler out, and I can measure from the center of this. So right now, the center of this one is at about 18 centimeters out. And it's still reading. It's dropped off. Oh, it's dropped off a lot. So it's not reading much at this point. Let me see. Let me put this back in here. Make sure that we got a few hundred millivolts here, and it's down to, well, here it's down to 100, and it's down to 30. It's down to 1. Well, actually 3. I exaggerated. It's down to that's about it. 2. 1. So we'll see how far out we come with that. We're going to be making measurements from the central plane here to the central plane here, so that distance between them, and my ruler's only 30 centimeters long. I'm hoping that's going to be enough that I don't have to go get a meter stick, but maybe I will. Right now, yeah, we're about the limit of the ruler, and that's actually about where this thing is zeroing out, so should work fine. Yeah, let's take a look. I don't think we quite talked about the rest of this. So the definition of mutual inductance is based from this formula. It says that when we vary the current in the primary circuit here, that a voltage gets set up in the second current. And that voltage is proportional to the rate at which the current is changing. So it's proportional to d I dt, and that there's going to be a proportionality constant, and the proportionality constant is what we call the mutual inductance. Now there's self-inductance going on here also. This is like a transformer, and so there's self-inductance on this side. The charges that are oscillating here are having an effect on all the other charges. There's self-inductance going on this side, but then there's mutual inductance happening. This is having an effect on the charges here, and once these are in motion, these are going to have an effect on the charges here. And we can set this up as a matrix, which we're not going to do, and show how these things are related in, for example, a transformer. All right, now let's start back with circuit 1. Let's say that I got this power supply, and it's oscillating at 377 radians per second. I could write the current as a function of time as some kind of a peak current, let's call that I naught, times the sine of omega t. So we'll just pick out a sine. We could have picked out cosine. Sine seems fine. Now, if that's what the current is varying like, what we're actually interested in is what is d I dt. What's the rate at which the current is varying? And we just take one time derivative to come up with that value. So that's going to become omega times I naught times the cosine of omega t. Now what that tells me is this voltage, remember the current over here is varying like a sine function, but the derivative is varying like a cosine. That means the voltage here is varying like a cosine. Now what I'm going to do is I'm going to copy this formula over. I'm going to say V2 is equal to the mutual inductance times di1 dt, and I'm going to copy this expression in. So that says that the voltage that we end up with in the secondary depends on what the mutual inductance is. Now that's going to depend on, again, how many loops they have, how many loops are here, how many loops are here, what's the length here, what's the length here, what's the dimensions, how far are they separated. So that's all going to get put into the mutual inductance. And then it's proportional to the frequency. Now, the faster I oscillate this, there's an acceleration of the charges, and that's proportional to the frequency that we're oscillating at. So this is what, I got this V in this acceleration listed here. The V here is reminding us that when I have a current, the current's telling us something about the velocity of the charges on average. Now they're not moving with constant velocity, but there's kind of an average velocity at which the charges are moving. And since this is varying, there's also an acceleration. So di dt is going to tell us something about the average acceleration of the charges. And it's the electric fields generated through accelerating charges that create this effect. So all the coefficients out front of the cosine, that's what we're measuring with the voltmeter. That's what the voltmeter is going to be measuring here. So I can take those constants, set them equal to the voltmeter, and solve for the mutual inductance. So I can actually get a formula where I can solve for the mutual inductance. Now the V naught, there's a V naught here, which is a peak voltage, and there's an I naught here, which is a peak current. I can scale those back down to RMSs, because that's what my voltmeter and my ammeter are going to be reading. They're going to be reading RMS values. So I'm going to write that as VRMS measured for circuit 2, and IRMS measured in circuit 1, and then there's a factor of omega. And that's how I calculate the mutual inductances. So what I can do then is I can start off with these two completely overlapped, and then move out 2 centimeters at a time out to 20 centimeters. And I'm going to keep track of the currents. Now I'm not expecting the currents are going to vary that much. When I was playing around with it before, I didn't see the currents changing so much, but the voltages change significantly. And so as the voltages drop off, that's going to be a way to determine how the mutual inductance drops off. Now here's a data table. Here's a graph. So all the results are really already contained in this data table. So there doesn't need to be any, well, let's say this. Let's say that we want to work from the data table here, and we want to graph this. And to graph it, I've got to do mutual inductance as a function of x. And here's all my data plotted. So the green is my data. Now there's a fit line here, and we should talk a little bit about the fit line. This could be a really complicated function. So we don't expect this is going to be some simple function. There's a couple different approaches you could take. My first suggestion is just carefully do a hand-drawn fit function. Just draw something that is smooth and curved so that it represents the data pretty well. Not a zigzag. Not, oh, this data point, then this one, then this one, then this one, this one. If there's a smooth curve that kind of fits all the data points, that's fine. But we're guessing that some of the data points are going to be shifted a little bit off of the main pattern. So there's probably going to be a bit of a mismeasurement here or there, because we have limitations in measuring our distances, making sure that the axes of the two solenoids are aligned. So we've got these uncertainties that are coming in. Anyway, I would suggest you could do this by hand. If you do want to try some kind of a function, you could try a polynomial. You could try some kind of a polynomial and see what that looks like. Maybe you can get a polynomial to fit, maybe not. Maybe you end up coming back and trying to do it by hand in any case. Now, as far as doing a comparison, as far as a result that we can compare with something, there's no accepted values. I don't have a list of accepted values for this. What I have instead, or what we can do instead, is we can do a theoretical calculation based on what we've been doing in class. So here's our formula for mutual inductance. Now this is an idealized formula that says that the two loops of wire completely overlap each other. Okay, so that's what that formula is coming from. Let's see if that's a good approximation or not. What do you think? when we're right here at the center, are all the loops of wire in here completely contained within all the wires outside? And I'm going to say no, they're not. So it's a very rough approximation. We're just trying to see if we get roughly something sort of similar. We'll see. Maybe it works. Maybe it's the same order of magnitude or something. But this is the formula we work from. And then I just wrote down. I did a series of measurements. I got out my ruler, measured some lengths of each of these, measured the radiuses, and then either counted the number of loops or read the number of loops. The big solenoid just says 3,250, and I'm just going to assume that's the correct number, 3,250. So, so that's it. We've got the N1s, the L1s, the R1s, the N2s, the L2s, the R2s. We can plug those into the formula. We've got the electromagnetic force constant. We've got C, which is our speed of light that we've been using. And so I would say that we want to do a comparison here. Uh-oh. I really don't have room. Well, let's see. So we'll do a measured value of M. Now, the comparison's not really going to work very well at these larger distances. Our best chance of getting an idea of whether or not these numbers match up is going to be with this configuration. So we're only going to take that one measurement right here. So the measurement that corresponds to complete overlap of the two solenoids, that's the one that's going to get compared with theory. So there's going to be a measured value for M. There is going to be a theory value for M, and there is going to be a percent difference. Okay, I fit the data table in there, just barely though. All right? So that kind of takes us through the whole lab. We could take a few, let's do this maybe. Let's take a look and maybe take a few close-ups of the setup and see what's going on. I don't have it turned on right now, but let me do this. So, just to get a close-up look here, here's the power supply. Again, we're plugging into the 6.3, where is that number? 6.3 volt alternating current source. The red lines, the red wires are my primary circuit, so it's all color coded. And the primary circuit includes an ammeter right in here. Now, the ammeter timed out, so it's, let me see if I can get this back. Okay, it's set to, ooh, do I dare turn this on? There we go. So right now I'm getting 23 millivolts is what that's reading. I've got the solenoids set up here. Now right now I was getting some higher voltages earlier. Right now I'm getting a couple hundred. So I'm getting 193 millivolts. I don't know if I have this completely aligned. Let's see if we can get something higher. And then the other thing we want to check here is, okay, I'm going to bring this out, and let's get a look at how the voltage drops off with distance. So you could see, oh, you couldn't see what I was doing. So I was actually moving this away. So as I move it away, the voltages were dropping off. I guess the only thing you guys could see was the voltmeter dropping off. But that's kind of what the setup looks like for all of this. So again, this is the mutual inductance lab. If you guys have questions, stop by and we'll get all of those answered.